recording now. My screen is not shared. That's not the order to do this in. Whatever. Okay. It's fine. We fix it. Hello. Welcome. I'm Emily. And today we're going to prove these two sets are equal by showing that one side is a subset of the other. You may or may not remember that this was homework 3, problem 9. And I sort of suggest you don't go look at your solution for it right now, but then come back after this video and go look at what you did. Especially if you made any mistakes, we don't want to make them again. But if you feel so inclined, I know you're going to do this, but you could stop the video right now and draw out some diagrams of these two sets. Like, can we convince ourselves that this is even reasonable to prove is true? I mean, I guess they told us to, but we should think about like what parts we shade in, and can we just Venn diagram convince ourselves? Again, I really recommend you do this. None of you are doing that right now. I know you aren't. It's okay. I accept it and move on. It's fine. Let's get about to proving this. I first want to touch on why we even can prove this by showing that one side is a subset of the other. Like, why does that even work? If you feel like you got a good handle on why that works, feel free to skip ahead a little bit in the video. Else, join me over on this side of the screen with some ugly curly braces. And let's think about what being a subset means again, because it's really easy to forget, at least for me. And I often draw this out and think about, okay, it means that if there's an element in this left-hand side, like say this element A, it better also show up in this right-hand side. It's got to be there. B also needs to be here. And then we could have something extra, like C. That's okay. If we draw this out in pictures, this looks like the left-hand side is in here, right-hand side is this bigger one. If the dot is in the left-hand side, and it's definitely also in the right-hand side. These are sets, by the way. I'm just calling this left-hand side set and this right-hand side set. And if we go and think about the other direction, then we need every element over here to be over here. So we no longer can have this extra C floating around, because C better also be in here. So we first had this circle. I'm just going to switch to L and R. And now we have this circle. Sort of almost like if we said X is less than or equal to Y, and Y is greater than or equal to X, X must equal Y. The same kind of thinking here. These must be the same circles. Every element that's in the right-hand side must be in the left-hand side. Okay, that helps us a lot in figuring out how we're going to go about proving this. So we just said we need to prove, you know, both directions of this subset. And we can just pick one to start with. I'm going to pick this one. So this is what I want to prove in blue. Let's pick a different color. And now we got to start our proof. And what kind of proof is this? Okay, when we're not sure what kind of proof it is, we got to go back to the definition. We're trying to prove subset. And what is the definition of subset? We just said any element that is in this left-hand side has to be in this right-hand side. Any element. Let's think back to how we translate English to logic. That's got to mean for all elements in the left-hand side, that element also exists in the set on the right-hand side. That's a for all proof. How do we prove a for all proof? We get ourselves an arbitrary element. If that phrase makes no sense to you and you're like, I've heard the word arbitrary a million times, Emily, but y'all just keep using it and it makes no sense, please go watch lecture 5 again, where this is introduced. Please come to office hours about this, and even ask us to make a video. I don't want this video to be super long, so I'm not doing it here, but that's a really important concept. Please, please, please seek us out. We would love to talk to you about it. Okay, Moving on, as if we do know this word, we gotta assume some arbitrary x is an element of B minus A union C minus A. That's our assumption. And what do we want to prove again? Where do we want to get this to? Oh yeah, we want to show, wow, I'm struggling down here. X is an element of B union C minus A. Wow, that is an ugly A. Okay. This is where we want to get to. We got a lot of space to cross, don't we? We did all this thinking, and now we still have to do all this more thinking. But it's okay. We know how to do this thinking. You're probably like, Emily, shut up, but it's okay. Let's look at, just like natural deduction, let's look at what operators we have. We have x is an element of B minus A union C minus A. This union symbol is an operator, and a pretty important one. So what information does that tell us? Is x in B minus A and C minus A? X is either in the left-hand side, is an element of the left-hand side, or is an element of the right-hand side, or both. What does that sound like? That sounds like an or statement. How do we deal with or statements? We do an or alone. Or really, we do proof by cases, right? Because either the left-hand side is true, or the right-hand side is true, or both. So we kind of want to say, okay, case one, left-hand side is true. X is an element of B minus A. And then we have a case two. Case two. X is an element of C minus A. Wow, please excuse my handwriting. I hope you can read this. This setup right here is very similar to that or elim assumption boxes we did with natural deduction. Assumption box assume the left-hand side, assumption box assume the right-hand side. And we need both to reach the same conclusion. What's our conclusion here? This bottom statement. We want to show this thing. Okay, we gotta get started. Let's look at case one. Seems like a fine place to start. X is in B minus A. What in the world do we do with that? Well, we have an operator. We have a minus sign. What does that mean? I suggest if you're like, I don't really know what to do with this minus sign, you go back and look at definition of set minus. But what that says is we want everything in B that is not in A. We sort of like cut out all the elements that are in A from B. And if we write that in words, or this isn't really words, I guess there's a couple, we can say X is an element of B and X is not an element of A. That's what X being in the set B minus A means. Definition of set minus. Okay, I'm gonna run out of room, but imagine I wrote the definition here. So now we're at this step. We used all the operators we had to work with, but where are we trying to get to again? Oh yeah, we want X is in B union A minus, oh my god, X is in B union C minus A. Okay, we can kind of think about how to write this out too. This means X needs to be an element of B union C and X is not in A. Definition of set minus, doing the same thing. And wait, we already have X is not an element of A. Clutch. We can ignore that part, we already have it. Lovely. So we just need X to get to, we just need to get to that X is an element of B union C. Okay, well X is an element of B. How can we make this jump? Well, what does it mean to be in B union C? That means X is in B or X is in C. Or statement, or intro. How do we do an or intro? Well, we have X is in B, so it better be an element of B union C. And we have X is not an element of A from before, so X must be an element of B union C minus A. And wait a minute, that's where we wanted to get to. Heck yeah. Like, actually, we did it. We done did do it. Life is great. We didn't do case 2, and I'm actually going to not, because if we think about it, if we just wrote, instead of writing B here, in case 1 we wrote C, we would do the exact same proof. So we can just copy it over. Same idea. And now you might be like, Emily, this is like a list of these statements, and like I get your logic following through, but like, how do I actually write this in a proof? And this is how you could actually write it in a proof. I would probably write a line that says X in B, so X in B union C. This is getting really hard to read, but I added this little line right here, X in B, so X in B union C. And then maybe I come down here and again say by definition of set minus. But like, that's really it. The logic on its own is fine, just a couple words to help speed things along. Let's go look at what the instructors did. So let's make a different color. This is the very wordy solution that got published on Canvas. And let's just think through it to see how it fits with what we just did. Okay, well first they said we gotta show both these subsets, both directions. Okay, cool. And then they said, okay, we're gonna go this direction first. We said that too. And this is the assumption. We have this same assumption. Then they split up the union statement into this or right here. They picked case 1. This is the assume the former. That's what they're saying, assume case 1. They wrote out definition of set minus. They didn't even say they used definition of set minus. They really just said then. That's okay too. And then they said from the first of these assertions, which I would never write in a proof. I have never used the word assertion ever. But they basically said, because X is in B, then X is in B union C. That was like what this fancy language sentence does. And then they didn't even again write definition of set minus. They just said, we can conclude the thing we wanted. Like, this was all the steps we did. They just kind of threw in some fluff around it. So don't get hung up on this. The steps and going through them is much more important. I kind of glossed over in this middle part where they said without loss of generality. That's really the same thinking we did when I said, hey, case 1 looks just like case 2, except with a different letter, a B instead of a C. That's what this weird phrase means. I tend to not really use it in proofs. I would just rewrite case 2 because it doesn't take very long and it convinces me that my proof is good and all the logic works out. But if you feel like it, it's an option. Okay, I'm not gonna go through proving the other direction in this video because this video is already long, sorry. But it would be fantastic and great exam review and just practice to go and prove the other direction yourself. So remember, we need to prove this way. Try that right now, especially if this problem didn't go well for you. Try it without looking at the solution or what you did. And then take your work, go back to your old homework, see what didn't go so well there, and reach out to us with questions. Best of luck studying these next couple days. Please, please, please get some sleep. Make a cheat sheet. Get some ice cream to eat after the exam if you're not lactose intolerant. You all will do great. Thanks. Bye. Oh, wait, I'm not leaving. Stop share. Stop share is the button I want. Pause. No, stop. Stop. Yes.